I'm here to introduce Eugenio. So Eugenio spent his undergrad and graduate years in Pisa, Italy, where he studied physics, more specifically theoretical physics. From there, he went to Marseille, France, and he spent 2 years as a postdoc there. Currently, he is a postdoc working in Canada, but the reason why he's presenting here is that he's spending 1 week here talking with some other, I guess, graduate or postdoc students. And right now he's working on a project to find on the discreteness of quantum geometry. And from what I know, he really likes it here at Cal. He's enjoying the weather. And without further ado, here is Eugenio.
Thank you very much for this nice introduction. Thanks to everybody for coming. It's a great pleasure to be here. It's a wonderful place. So in this lecture, I would like to tell you about black hole entropy and the shape of the quantum horizon. I decided to divide the lecture in 2 parts. The first part is about theoretical results of rather older, of the 70s, 80s, but still very intriguing. And the second part is on current research. So the question I'd like to discuss in the first part is what is the horizon of a black hole? And the reason why I'm interested in this question, why it is hot, is because people working in quantum gravity have the idea that answering this question can provide a clue to the quantum structure of space and time as well as space. So the puzzle is what are the horizon microstates that explain this fact that the horizons are hot. And there are various attempts, various research directions. I'm working on one of these research directions, that is loop gravity, and I'll give you a picture that is arising from this approach. So let's start from black holes. As you know, it's the last stage of collapse of matter when pressure is not able to sustain gravitational attraction, and the other result is a space-time without matter with the curvature that diverges the singularity, and this singularity is hidden behind an horizon. The size of the horizon is larger if the black hole is more massive. Now, these objects are in fact out there, and there are many. I read in the news recently that here in Berkeley, astronomers have found one of the most massive black holes, 10 billion solar masses. For a black hole of this size, the horizon radius is huge. Here in this picture you can see compared to the size of the solar system. Now, there's strong theoretical evidence that this horizon has thermodynamic properties. These are results that are started around 74 with Hawking, and involve many ideas in theoretical physics, from general relativity to quantum field theory, thermodynamics, and yeah, I won't give you a derivation of this result, the derivation of the temperature, but I want to ask the question. The question is, I'm telling you that the horizon has a temperature, black hole has a temperature. How do you measure the temperature of the black hole? Well, with a thermometer. And the way to do it, the thermometer is you consider a black hole coupled to an electromagnetic field, so the way that it reaches equilibrium, and you measure the temperature of the electromagnetic field at infinity. You measure the radiation at infinity, and you find that this electromagnetic radiation at infinity is thermalized at a temperature that scales as 1 of the mass of the black hole. Now, this result is puzzling. This result is puzzling, and the reason is that if this is the temperature of the black hole, this is the temperature associated to a classical solution of the classical equations for gravity, classical equation of general relativity. And now why is that? Why is it just a single classical solution as associated with that temperature? If you compare it to the situation with Maxwell equations, you can consider the classical solution corresponds to a static electric charge, and temperature is 0. If the charge is accelerated, you have emits radiation that is certainly not thermalized. In many particles, the way that they thermalize. as that here, with a single classical solution, we have a temperature between. And this thermodynamic property is not the single property of these solutions. There's much more. You can associate an entropy to these horizons. Now, in the next slide, I want to give a short derivation of this entropy. Use just 3 ingredients, all to be familiar. The first one is the closure relation, the first law of thermodynamics. The second one is the one that I just discussed, Hawking temperature, temperature as a function of the mass of the black hole. And the third one, the energy of the black hole is equal to its mass in units C per watt. So we'll just use it, compute the entropy as the integral of inverse temperature in the energy. We find that it scales as mass squared, but in fact this result has a geometric interpretation. It turns out that the answer is it scales with the area of the horizon. Now,
what was that formula that actually make the temperature for a star, the order of solar mass? What was that formula actually make the temperature?
10 to the minus 8 Kelvin for a solar
And
mass.
-6?
Minus 8 Kelvin.
What's that?
Minus 8 Kelvin.
And -8 Kelvin.
Yeah, so I'm saying it's soft, it's not actually, it's quite cold. It's quite cold if we are far away. But there's a weird property of equilibrium, thermodynamic equilibrium when gravitational field is strong. It is for standard systems at equilibrium you have that the temperature is uniform. For strongly gravitating systems, you find that the temperature is not uniform. There's this picture that you can have in mind. Suppose that you have 2 subsystems and they want to reach equilibrium. And the way to reach equilibrium is to, for instance, exchange energy via electromagnetic radiation. But now these 2 pieces can be at different heights. And when electromagnetic radiation starts from the one that is lower to the higher, it's redshifted. So the equilibrium temperature will be one where the gas is hotter at the bottom and colder at the top. And that's the temperature if you are at infinity. It's finite, it's smaller, it's non-zero. But if you are close to the horizon, suppose that you get close to the horizon at distance, proper distance L. To do this, you need to accelerate. You need an engine, you need to be in a rocket. Accelerate, stay at distance L into an acceleration that is 1 over L for this trajectory. Another way is just a rope and someone at infinity is holding you. So I'm speaking about a very big black hole like the one of the picture before, and the geometry near the horizon is quite the curvature is smaller, more small. You cannot distinguish it from flat space. And here you are accelerated, so probably you know this diagram. This is just, an accelerated observer, and the metric is the regular metric. Now, before I was speaking about the temperature of the black hole at infinity, you can ask what is the temperature when I'm at finite distance. And we found that, again, the black hole has a temperature, equilibrium temperature, and when you're close to the horizon, its temperature now is high. It's really high. It goes as 1 over the distance from the horizon. And, well, if you cook using olive oil, then you should cook your frying pan at 10 nanometers. So horizons are off, are really off, and we can compute again the entropy as seen from an observer that is close to the horizon. So again, as before, and now from a near horizon perspective, close to the relation is the same. The temperature now is the acceleration temperature. The energy, one has to be careful, has to use the appropriate notion of energy. There is an appropriate notion of energy here. It's the common energy at distance L. As the area and the acceleration, can compute it, and again you find again the same geometric formula. So the conclusion is that for a black hole there's an associated entropy. It is geometric. The Beckett side of the entropy is proportional to the area of the horizon. And this concludes the first part of my talk. Now I want to go to the second part, why it's hot, why it doesn't entropy. Because, as you can imagine, this is a puzzle now. If you find that there are thermodynamic properties, what is the statistical mechanics behind all this? And that's another question. So let me explain again. Let me stress what is the puzzle. I've been speaking about the entropy. In fact, you don't measure the entropy of a system. The thing that you measure is, for instance, heat capacity. How much energy you have to put into the system to resist temperature by 1 Kelvin. So it turns out that heat capacity is huge. For a solar mass black hole, is 20 orders of magnitude larger than heat capacity of a star of the same mass. So what are all the degrees of freedom that are there? There are CAT. What is the statistical mechanics origin of this entropy? There have to be microstates responsible for heat exchanges. And they cannot be under the horizon, because stuff that is under the horizon cannot interact with what's outside, cannot exchange it. So I would like to have a Boltzmann description of this entropy. And we need a theory. And there are many proposals around, many ideas, and I want to discuss just one. It's in fact a very old proposal. So this time, you see, we have been speaking, for instance, about Schwarzschild black hole, where the horizon is just a sphere doesn't have microstates, it's just one shape. But there is this proposal that the horizon, well, you notice that already at the classical level, the horizon is not something static. The horizon is something dynamical, something that couples to the environment. Suppose that you have your black hole with around the planets orbiting around. They will deform the shape of the horizon. If you have a gas around, there will be thermal fluctuations. And even if you don't have the gas, there will be quantum fluctuations in the shape of the horizon. And the proposal, the idea is that the horizon microstates, the ones that you should be counted into account for this entropy, are in fact fluctuations in the shape of the horizon. Now, you can try to make this idea more precise. You can try to do a calculation in quantum field theory, a perturbative calculation. This, in fact, has been done. It turns out that the idea is working quite well. You find that the entropy is proportional to the area of the horizon. Now we would like to compute the proportionality equation. And to do the calculation, we have to introduce a cutoff, a regulator, not polaric cutoff, for fluctuations of small scale. You find that this coefficient is scales as the cutoff square. So if you want to remove it, the entropy just diverges. And that's a problem. Maybe that's not a problem, maybe that's an hint. It's an hint that the theory requires a physical regulator. It requires some new physics at a certain scale. It turns out to be the Planck scale. And the idea is that this can provide a clue on where to look for material quantum gravity. What are the kind of microstates that we should expect? Now, I'm working on this theory, on this approach to the problem, loop gravity. And this approach has a feature. It provides us very specific physical cutoff. It is on the form of geometry gets quantized. It has discrete spectra, and these discrete spectra don't allow any possible kind of fluctuations, only some kinds of fluctuations. And that's what I would like to discuss now.
How do you define loop gravity? What is loop gravity?
So it's an approach to a problem of quantum gravity where you quantize the metric.
What?
You quantize the metric of space. And what you find in this approach is that you can introduce observables like the volume of a region of space and compute its spectrum. And you find that the spectrum of a region of space is discrete. So this is a kind of hint that there's a physical cutoff. Can compute this spectrum. It has a volume gap. The lowest non-vanishing volume is of the order of Planck volume. You can also compute the exact states. How to define the theory is not immediate. I won't introduce the theory. I will only use some of the features of this theory. In fact, as a first step, I won't even use all the features of this theory. I just want to focus on a simple problem. It's relatively simple. The question is, how many shapes can a sphere have? So what I mean is, fix the area, and you count how many metrics you can put on S2, Riemannian metrics, so that the area is fixed. So calculation you should do is the integral of different invariant classes of metrics of the delta of the area minus the expression of the area in terms of the metric. And now you see that you would like to do this calculation, but this is something that you have to define. What is this measurable metrics? A way to define it is to introduce a cutoff and find that this number of shapes grows exponentially with the area, so that the entropy, that is the logarithm of the number of shapes, is proportional to the area. So this situation is exactly the one that I was describing before. It's a calculation where I introduce by hand a cutoff, but in this situation I find that when I remove the cutoff, the entropy diverges. Now, what is the cutoff loop quantum-gravity provides? I should tell you that there is a concept in quantum-gravity. It was introduced earlier, in fact, in the 90s. People were not speaking about shapes of the horizon. People were speaking about states in this theory. States in this theory describe a quantum geometry, and they are represented by some network on the spatial manifold. And when there's a horizon, we call it, in fact, that there's a boundary. Topology is 2, and this network has links that pierce the boundary. And in use on this boundary, a field theory, topological field theory of a specific kind, and it is under control, and to each puncture there is associated a spin representation as well. And people counted number of states in this theory and found that the entropy is proportional to the area of the horizon. Now, something that has been clarified only recently, in fact in the last year, is that the states that people are counting in this approach can be interpreted as geometries of the horizon, quantum geometries of the horizon. So not smooth geometries of this kind. There's a semi-classical picture for the kind of geometries that arise. It is tessellations of a sphere. Tessellations of this kind. Now this is a semi-classical picture, or what arises in the limit h bar to 0. So let me describe first this. So this geometry is obtained in this way. The data are area of each one of the faces, and this area is quantized this way, for J is spin. And normal at each one of the faces, unit normal. And the fact that this is a closed sphere is encoded into this closure condition. It tells you that these normal vectors sum to 0. Now, this is a semi-classical picture. If you use this data, you can reconstruct this geometry, but this was found long ago by Minkowski. What is found in quantum gravity is a quantum version of this, where these normals are in fact angular momentum, so they don't commute. So the result is that not only the area is quantized, but also the angle between two of these spaces, the extrinsic curvature, also this is quantized. So there's a quantum discreteness, also a non-commutativity, because you could measure angles between two faces, these two, and these two. And these are associated with two operators, two angular operators that don't commute. So you cannot diagonalize both of them at the same time. There are uncertainty relations satisfied, and this will this shape more fuzzy. All this is introducing a cutoff, but now this is not an artifact, it's not something that's being introduced by hand. This is to be considered as a physical cutoff. So these are the microstates. So these are the candidate fields that are there and could oscillate and explain this thermodynamic behavior. I told you about the microstates, but still one has to do calculation. Show that if you choose your ensemble, you fix the microstate, you count how many states you have, you get something that explains the entropy. So here, the macrostate that I would like to fix is one that was partial. I won't require that spherically symmetric, I will require just the total radius fixed. While the microstates are the ones that I was discussing before, this accelerated geometries. And you see that most of them are not so nice as this one. Most of them will be spiky, elongated. While most of them, some of them, like the gas in this room, certainly it's the molecule. Certainly there's a discrete distribution. Molecules could be all in a corner of the room. That's not the most probable state. But certainly you cannot assume that there's a continuous fluid with an homogeneous distribution. Okay, so these are the microstates. When you count them, you get number of states exponentially larger with the area. And there are two questions. One is, how do you count them? Looks like a difficult problem, counting problem. Another one is why you should get as most probably configuration with this spherical knowledge. And so how will you use it? I understand that people in statistical mechanics have a standard strategy to address this kind of problems. The first question they ask is there another problem that is equivalent to this one, can we map this one, where the answer is already known? And it turns out that there is a problem of this kind, and it's the problem of counting conformations of a polymer chain. And the mapping of this problem to the polymer chain problem is of the following kind. Yeah, this geometry is described in terms of these normals that sum to 0. So you have this porcupine of all these vectors sum to 0. But you can choose an ordering. Take one, sum to another one. So you get this closed chain, closed because the sum of them has to be 0. You are counting conformations of this chain. So in this mapping to each face, associate a monomer. The area is the length of a monomer, and the normal is the direction. The closure is the fact that this is a closed chain. And one can ask the entropy, why is the entropy finite? Well, for a polymer, the reason why it's finite is that there's some physical cutoff. It comes from monomer chemistry. It's not a continuous chain, it's made of small monomers that are rigid. And the other physical cutoff is this quantization in the area. You can compute the entropy. There is proportional to the length. When you map it back, you find an entropy that is proportional to the area. And there's something that one learns when one studies the equilibrium of these polymer chains is that most configurations are crumpled. If you have a long polymer chain, in fact, when you put it in a solution, it crumples down to a small size. In directions that are randomly distributed, and when you map it back, you get a geometric configuration that is in average spherical. Now, I'd like to pose it as a question. So, do you know what happens if you take one of these? You can make one of these polymer chains easily. We talked about this with Hal yesterday. We bought paper clips. You can think of them as our monomers. And you can pick many of them and join them together so that you get a polymer chain made of paper clips. It has a certain extension, and if I put it here on the table, clearly there's no reason why it should crumble. It just remains the size it is. But the statement that one learns is that when this polymer chain is in a solution, it crumples down to a size that, do you know what is the size? if it's made of n paper clips, what is the size, the final size? Do you have a guess? It gets short. It's something you know. The other question is why it's getting short. We need something that thermalizes the system. So to show this, I need 2 volunteers. Are there 2 volunteers to play this film?
Come on in.
Please. So we talked about this. Let's try to find some system that could thermalize our polymer chain. So what we need is just load it. We have our polymer chain, and I put it here inside. I don't put it properly. And there's something that you can do. It is just shake it and see what is the size that you. If you shake it strongly without like this. Yeah, and you can measure how long it is. Just comparing it. What you find is the thing that you know. It is that the size scales as the square root of the number of paper clips. Yeah, this one was quite long, was 26 paper clips. Yeah, and yeah, so is it showing something? Well, the thing that it's showing is that to reach equilibrium, we need something that thermalizes the system. So our question here is, what is thermalizing our system? I've given you the method. Thank you very much. We need something that thermalizes our system. And here I've been telling you about microstates, about conformations, but not about something that thermalizes the system. So in my last slide, I would like just to mention something that is recent, that is to identify what thermalizes the system, we introduce notion of energy. And there's a notion of energy here, which is if you have a stationary observer at a certain distance, the Hamiltonian can introduce at the quantum level, that is just the generator of this accelerated observer. And now you can compute how many states you have at given total energy. You can study the microcanonical ensemble. Is number of configurations of energy given as sum of all the states compared to the known stage. This is something that you can compute, especially in this limit when the distance from the horizon is small compared to the horizon values, but large with respect to the Planck scale. The Boltzmann entropy is the term in terms of this number of states. Once you have Boltzmann entropy in terms of the energy, you can compute the temperature. Just inversely derivative of the entropy with respect to the energy. And you find, again, this acceleration temperature. And now you are deriving it from the statistical mechanics, the quantum statistical mechanics of these microstates. So the quantum horizon is optimal. If L is really small, there will be corrections. That's another problem. Can be interesting, something. So let me just conclude. The main 2 messages are that Berkeley horizons are hot, and that they can teach us a lot about the microscopic structure of space-time. Thank you very much for your attention.
Are there any questions?
Can you go back to the last slide and go forward?
How does this generalize to black holes?
Yeah, very good question. So, if you consider just this picture, yeah, we are close to the horizon. And in the case of Schwarzschild, what you see is a ring regularity. Now, in the case of a rotating black hole, to be stationary, it's not enough that you are close at a fixed distance. You have to be rotating the black hole. And again, I will see a ring regularity. Unless the angular momentum is not large, so that it is a stream output.
So would your closure relation still hold for a black hole? Because it's
Yeah.
only for that spherical, no?
So if you come back here, black hole has the deformed shape. It is in fact for small angular momentum inside the ellipsoid, but it's still closed. So the sum of the normals is the same.
How are you actually choosing the shape of the discrete bits on this horizon? Like, do these polygons can they be anything, or do they all have to be like triangles? Or?
Yeah, very good question. So it's complicated. It's a complicated problem. So in terms of the data, it is area normals that satisfy this condition. The shape is completely fixed. It's something that goes with. But reconstructing it is not easy at all. In fact, it's something that you can do numerically. And you find that the shape is doesn't have to be a triangle. In fact, it's almost never a triangle. In fact, we looked at this numerically and found that if the number of patches is, the number of trees is small, if it's 4, then it will be a triangle. If there are many, the typical shape will be of this kind. Each vertex will have 3 edges, so at most 3 faces will meet at a vertex, and each face will have, in average, 6 sides. And this is with for the 100 faces. The other thing that one finds numerically and also analytically, certain expansion, is that you see there's a distribution for each face can have different areas, but they are quantized. So one can ask how many spin 1 up of them there are, how many spin 1. There are mostly spin 1 up, some 55%, some 30% of spin 1, with the rest exponentially suppressed. So they are small. Translate.
So does this relationship where these JAs are like quantum numbers, this comes, you said before, I think, that it comes from the fact that you're treating these area normals as like angular momentum. So they don't commute and they have this angular momentum algebra that leads to this. So so in what sense is an area normal an angular momentum?
Yeah, good question. So this is something that comes out from group quantularity. So it's something that you can consider as a result of quantularity. The fact that the geometry of this patch has the same algebra as angular momentum. I don't have a simple answer.
Something to look at.
I don't know.
I mean, there's an old argument of Roger Penrose's, which is fun. I was describing this to somebody earlier. You take a bunch of small spins and you add them all up in one direction. So you get a clearly defined direction by all the sum of those spins. You do that again, so you get a second direction. Now you take one of the small spins off and let it interact with the other one. Right? And through that interaction, you'll get the usual quantum mechanical relation, that it adds with a cosine theta, the angle between them. Well, Roger's idea was to say that this tells you the geometry of space-time. It tells you the geometry of space because you're getting exactly the Euclidean angle between these two directions from the interaction of these angular momenta. So that was the original intuition behind this. It comes out in a much more technical and precise way in the full theory.
I'll probably have to look that up too.
Okay.
But that was cool.
So is the only motivation for loop gravity that it solves the counting problem of the black hole stuff?
In fact, this is something that it's come out after. It was not a motivation at all. It was starting with a different motivation. It was what happens if you quantize general relativity. Looking at it now, one of the strongest arguments to me, one of the tests of the theory is this one. There's a problem, and we see it's there, we understand it, and we look for a solution, and the theory is providing a solution in a very nice and simple way. So I consider it mostly as a test. A test and something that can provide new effects, because it's same classical regime, But for a smaller black hole, there will be quantum corrections. The question is, are they black body? Do you get black body radiation? Do you get corrections to black body radiation from small black holes? We don't know. We don't know yet.
You said a moment ago that about 55% of them are half and like go smaller. Is that known empirically, or like is that a result from loop
Has
quantum
been
gravity?
found both ways. Just sampling points in free space and analytically in an expansion of large total area compared to the area gap. So the statement is exponentially suppressed in spins. Yes.
So I have a very naive notion of what temperature actually is, and I think it is the energy of all these different particles, and that's temperature, right? So I'm not quite understanding what exactly is causing this temperature. What is hot in these black holes?
Yeah, it's a very good question. It's a very good question. In fact, here recently was something we were not understanding. In fact, we were finding these microstates. Then you can ask, suppose that they are thermalized, what is the distribution that you find? Exactly as with the paper clips. You have the microstates, but if I put them there on the table, there's no reason why they should crumple and form a small clump of polymer. And it is actually an open question for long. Now, here in the last slide, I'm pointing out something I'm quite excited about. Is something very recent. It is you don't have to fix the temperature of the system. You don't have to put the system into a button. You can simply fix the energy of the system. Count how many states the system has of the temperature. So I'm working in the microcanonical example. I'm working with an isolated system, and I'm asking if it can thermalize by itself. And in thermodynamics, you know that this works. If you have a box, many particles have fixed energy with generic initial conditions, and you wait enough, you find that it thermalizes, and the temperature is something that you can compute in terms of its energy. And here we're doing something similar. There's a reason why this is even more interesting for gravity. Is in the gravitational case, in fact, you cannot fix the temperature of the system, because otherwise the system would be unstable. Something that happens already in classical ordinary gravitational mechanics. It happens already for a nebula, for a distribution of gas, on the galactic side, that the capacity is negative. So the system is unstable if you put it into a thermal buffer of its temperature. But on the other hand, the system is isolated, and you can study it in the microcanonical system. Here we are doing something very similar, not for a classical gravitating system, but for these microstates of gravity. So the answer to your question is that the system is thermalizing by itself as an insulated system.
So is it the space itself that has this heat that you can measure?
I would say you are fixing the energy of the system, and then you are asking what is the average energy of each one of the atoms of this system. You find that there's an equipartition of energy, and you can associate the energy of each one of its atoms to a temperature. The way you compute the temperature in this microcanonical ensemble is you have the entropy at given energy. The temperature is obtained as addition of the entropy with respect to the energy.
I like Alan's question a lot. I want to ask it another way. So if we're going to fry this egg, how are we actually going to do it? What's going to happen?
It's something that has been passed. I've been very confused for long, and to me this sounds like an answer. And in the case of what happens to this frying pan, you are putting it at a fixed distance from the horizon, and you are holding it here, and you can measuring this temperature, a thing that you can ask is, what is the energy that you would measure as an accelerated observer? And the energy is something that was known since long, is this common energy, but then you should ask, it's the energy of what? And classically, it's not clear the energy of what. Yeah, an answer that we are giving is if there's an equipartition of energy, then and there are n microstates, energy divided n is the energy of each one of the microstates that you can identify with KT. That is the temperature.
Are there situations where this gives different predictions from the classical formulas you gave in the first half?
Say it again.
Are there situations where this gives different predictions from the classical formulas you had in the first half?
Yeah, that's a very good question. So this calculation is done in this regime. You are close to the horizon, but you are still far from the translate. Clearly, there are corrections when you get closer to the translate. I don't know in which directions we haven't computed it yet. I think it's something interesting, something that can be phenomenologically relevant. For instance, a question you could ask is, can I get closer than one Planck length to the horizon? What does this give a saturation of temperature? Is there a maximum temperature that I can reach? I would say, yeah, there will be corrections. I don't know what kind of corrections.
So what assumptions do you have to make about the way a chain crumples for you to prove that the average length after it crumples is the square root of the number of lengths?
You don't need much. You can prove it for a chain that has joints that are free. It's called a Gaussian chain. But it happens that the behavior is more general. Suppose that you have a chain where the angle between every two of the monomers is fixed, as often happens in certain polymers. Then you find out that on a larger scale, you can get effective longer monomers that behave completely as frame. And you find that the system, that in this case, typical system behaves in this way, is DNA. The system crumples to a size that is the square root of the number of these effective monomers. So the answer is the behavior is rather general.
Please join me in thanking our speaker if there are no more questions.
You should all come back on Tuesday when we have the next lecture already. We'll be on dark matter from Professor Bob Jacobson. See you then.
Okay, it's good.